may be wondering how to use the information we presented on algorithmic complexity and efficiency in practice. Well, it's hard to give general advice because most issues that arise are problem-specific, but I can give you some pointers. First of all, start by solving the problem without thinking too much about efficiency. Just get a solution that works for a small data set and then feed it larger inputs to see whether that first solution is fast enough for the kinds of inputs you expect to get. If it is, you're done. Congratulations. But if it's very slow, you'll want to decide whether it's worth spending the time required to speed it up. If you would spend more time tweaking the solution than you could possibly save in running the version you've already got working, then it's not worth it. But if you expect to use this program many times and potentially run it with inputs that are large enough to slow down the program until it's impractical, then you have work to do. The first thing you should do is locate the part of your program that's taking the most time, which is sometimes known as the bottleneck. Of course, sometimes it's obvious. If you have 4 nested loops each iterating 10,000 times, then that's your problem. But if it's not obvious, you need to profile your code. Profiling in programming is a good thing. It means identifying how much time is spent in various parts of your program to solve the problem. MATLAB even has a built-in tool for profiling, which it calls, appropriately enough, the profiler. But you use it by calling a function named profile, which is what you should look up in the documentation. The profiler shows you what lines of code are taking the most time and how many times various functions are being called. It's got an excellent interface too, which we'll look at in a few minutes, but it's not available in MATLAB online. That's unfortunate, but the fortunate thing is that most of the time you don't need the profiler to tell you which lines are taking the most time or how many times functions are being called, because if you wrote the code, you know it well enough to figure these things out for yourself. And frankly, figuring them out for yourself is more likely to give you helpful insights than reading the profiler's output. So before we look at the profiler, we're going to do our own profiling. You can do that by using tick and tock or time it to time your function or time parts of your function, and you can add variables that count numbers of function calls. Remember how we added that persistent variable to our first Fibonacci implementation to figure out how many recursive function calls it was making? That was profiling, and it gave us the insight we needed to make the code more efficient. So you should start with profiling, and then, once you've found the bottleneck, you may be able to use one of the practical techniques presented in the following lecture to fix it. On the other hand, it may be the algorithm itself that's the problem. What to do then? Well, the obvious thing is to try to come up with a new algorithm. Many times after you've spent time with a problem and solved it once, you can much more easily think of other, better algorithms to solve it. But there's a middle ground too, and that's improving the algorithm you've got. It may be that small improvements to the way the problem is solved will make big improvements in efficiency. We're talking about improvements that don't amount to a new algorithm, but in practice can greatly improve the efficiency of the algorithm you've got. Improving an algorithm to make it run efficiently in practice is the focus of this lecture. So how do you improve an algorithm? Well, you start by asking this simple question: is it doing any unnecessary work? Here's an example to illustrate the point. It's called rooting v1 because it finds roots of numbers and because it's version 1 of our algorithm. The function takes 2 vectors of the same length and creates a matrix A as output. We've eliminated checks on the inputs to focus on the algorithm itself. The output matrix A has elements that are products of various roots of the elements of the 2 vectors. For example, A23 is the product of the square root of the second element of V and the cube root of the third element of W. It finds the roots by calling MATLAB's built-in function named nth root. The implementation is just fine. It does the job and does it correctly. The nested loops indicate that it's an order n squared algorithm, assuming both input vectors have a length of n. Let's run it using two 1,000 length vectors. I'm going to time it with tick-tock instead of time it, because at this stage all I need is a rough estimate of the runtime, and time it can take up to 10 times longer than tick-tock. Okay, it won't kill us to wait 7.9 seconds, but since we know that this is an order n square algorithm, we also know that if we needed to do this computation for inputs of length 10,000, we'd be waiting 100 times longer, which works out to over 12 minutes. That's pretty slow. So, here's the question we need to ask. Is our algorithm doing any unnecessary work? Well, yes, it is. Consider the actual computation here. Here we compute the ith root of VII in the nested loop JJ. Instead of computing it once, storing it, and looking it up each time we need it, we compute the same thing over and over unnecessarily. For the example we timed, the lengths are 1,000, so that's a factor of 1,000 wasted computations. Let's change the code to eliminate that inefficiency. And behold, routing version 2. Here inside the outer loop, but just before it starts the inner loop, we pre-compute the ith root of VII and store it in X. Then for each of the 1,000 times that we need it in the inner loop, as we go through values of J, we just look it up inside X instead of recalculating it. Let's see if that helped. Sure did. It almost doubled our speed. But before we do anything else, let's do this. Whenever you make a change to the code to increase efficiency, it's a good idea to test the new version on exactly the same input that you used on the previous version and check that output to see that you get exactly the same result. It's not much of an achievement to save time if you don't get the right answer. But back to this almost doubling of our speed. It's not really all that surprising because we've cut way down on the number of calls to nth root. That's important because it's very computationally intensive. That just means that nth root takes a lot of time, but I suggest that you throw in the phrase computationally intensive now and then when you're talking about your program speed because it sounds more learned. I do it whenever I can. In our first version of routing, we called nth root 2 million times. In the second version, we called it 1,001,000 times, so just about half as many times. So it's no wonder that the time was cut in half, considering how computationally intensive nth root is and all. But is this the best that we can do? Remember, the right question to ask is this: are we doing any unnecessary work? Well, what about the calculation of nth roots for the elements of W? We compute a root for each one of the 1,000 elements of W in the inner loop. But since the inner loop is repeated once for every iteration of the outer loop, we're repeating each of these computations 1,000 times. Why don't we calculate all of the roots of W first, save them, and then just look them up when we need them in that inner loop, like this? The change is slightly more involved this time because we had to introduce an auxiliary vector, which we called RW, to store all those roots, and an auxiliary loop to compute them. And here we use them right here. And let's see if it was worth it. Holy smokes! An improvement factor of over 100. Wait, let's make sure that we haven't made a mistake. Nope, answers are correct. Again, we shouldn't be surprised. Now we call nth root only 2,000 times as opposed to 1,000,000. But why not a factor of 500 improvement, you ask? Well, that's because although we've reduced the amount of time spent in all those nth root calls, we haven't reduced the time spent using the multiplications. Thanks to the improvements we've made, the time spent in nth roots doesn't dominate anymore. We're still doing 1,000,000 multiplications in our nested loop structure, and that takes time. Because of the multiplications in the double loop, this is still an order n squared algorithm. But now we've eliminated all the unnecessary work. We're seeing an overall speed up by a factor of over 200 relative to the original algorithm. Not bad for a few extra lines of code. And now that we've improved our algorithm and tested it on relatively small inputs, we can test it on inputs that would have been infeasible before. Let's see how fast it is for vectors of 10,000 elements, which we estimated would take over 12 minutes for our first algorithm. 1.5 seconds instead of 12 minutes. Of course, increasing the input size by a factor of 10 increased the runtime by a factor of almost 50, but it's still a lot faster than 12 minutes. Pre-computing and saving those nth root values to avoid recalculating them is actually a general technique. We pre-compute and store information so that we can save computation time by not having to carry out the same computation multiple times later on. One way to look at this is that we trade off memory against time. We use more memory, but we save time. In this case, the extra memory was a really small amount, one vector of length n, but we achieved a speed up of 2 orders of magnitude. I'll take a trade-off like that any day. There's a line in this function that we've kind of glossed over. The first one. We know the size of A before the calculation and rooting begins because it must have exactly 1 row for every element in V and 1 column for every element in W. And in all 3 versions of rooting, we start by setting A equal to a matrix of zeros of that size. This step is called pre-allocation, and we introduced it in Lesson 6 of our first course, but this is the refresher we promised at the beginning of this lesson. We also do pre-allocation for the vector RW, but it's tiny compared to A, so we're going to focus here on A's pre-allocation. Sometimes it makes sense to set an entire matrix to 0 to provide default values when some elements are given specific values and some aren't. But in this case, as in most cases, we're doing it expressly for the single purpose of saving time. It saves time because it forces MATLAB to allocate all the space needed for A before we start assigning values to it. And we could just as well set it to 1s as 0s. It makes no difference what values we put in there because the nested loops assign a value to each element of A anyway. But it does make a difference in the amount of time required for those assignments. It makes a difference because as the nested loop runs, every time the size of A increases by a row or a column, the execution has to halt while the MATLAB runtime system allocates space for the larger A and then copies all the values calculated so far into that larger version. Is it a significant amount of time? Well, let's find out. Let's comment out the allocation line and run it again. Well, I know you've got better things to do than to wait on this to complete, so I'll jump you forward in time. Man, 410 seconds. It's almost 7 minutes instead of a second and a half, only because we didn't pre-allocate. That's hard to believe, but believe it. Failing to pre-allocate can result in a huge amount of unnecessary work, reallocating space and copying values for arrays inside loops. And when you consider ways to avoid unnecessary work, pre-allocation is low-hanging fruit. There's really no excuse for not pre-allocating, especially since MATLAB even reminds you to do it when you don't. Let me shift things a bit so you can see this little box over here at the top right of the editor window. It changed from green to yellow when we commented out the pre-allocation line. Let's hover over it and read the hint that pops up. Warnings found. Click to go to the next message. The box is yellow because this is a warning, not an error, which would be red. Let's click it and see what happens. It's kind of subtle, but a little bluish-green highlight appeared around A. Let's go hover down there and see what pops up. The variable A appears to change size on every loop iteration. Consider pre-allocating for speed. And there's a Details button. Okay, I'm game. And now we find that MATLAB has written a dissertation on the subject. I'll just read one little passage here. For large arrays, MATLAB must allocate a new block of memory and copy the older array contents to the new array as it makes each assignment. Programs that change a variable size in this way can spend most of their time running in this inefficient activity. That's exactly what happened when we commented out the pre-allocation of A, and MATLAB is telling you exactly what I told you. Maybe you'll listen to me next time. So we can save execution time by figuring out where needless work is being done and avoiding it. But now let's look at another approach to improving algorithms. As I mentioned, MATLAB provides a nifty profiler. Let's use it to profile our second version of routing on vectors of length 1000. First, we'll set up the vectors as we did before. Then we turn the profiler off to eliminate any profiling in progress, and then turn it on again. Then we run our function normally without using tick-tock or time it. And finally, we run profile with the viewer option. And up pops the profiler window. It shows the function that we just called and any functions that it called, which in this case is just nth root. With each one, it gives the number of calls, which is 1 for routing v2 and 1,001,000 for nth root. And it gives the times that they ran in two forms. First, the total time, which was 6.641 seconds for routing v2 and 5.808 seconds for nth root. These are tick-tock times. But in addition, it gives the time that each ran exclusively of the time during which functions that it called were running. So during the 6.641 seconds that routing v2 ran from when it was called until it returned, 5.808 seconds of that time was consumed by the 1,001,000 executions of nth root, with just 0.833 seconds remaining inside routing v2. And there's more. The name of each function is a live link. Let's click on routing v2. The first thing that we note is that there's a listing of the lines that take the most time. The workhorse here is line 6, which was executed 1 million times. That's what this column called calls means. But of course we knew that. And I must say that this is often the case. The profiler, instead of surprising me, usually confirms what I already suspected. It does a bit better than that, though, because it gives actual times, and more importantly, percentages. Clearly from this profile, we see there is no reason to work on line, say, 4, which consumes only 0.2% of the time. And there's one more thing to see. If we scroll all the way down, we find all the code for the function with annotations showing the time that each line occupied and the number of calls for each. So, for example, this workhorse line was called 1,000,000 times. And if you click any of these live number links, it highlights that line in the editor. There's more to the profiler, of course, but I've shown you the main points, and you can try it yourself sometime when you're using an installed version of MATLAB. Well, now let me show you another example for which the question, is my algorithm doing unnecessary work, can save the day. It's an example that lends itself to speed up without requiring the use of additional memory. Instead, it takes advantage of the characteristics of typical input to avoid unnecessary calculations. Consider a social network where people are identified by unique IDs, which are integers from 1 to n, and let's say that n equals 3,000. People can follow other people, and this information is captured in a cell array called follows. Element j of follows is a vector containing a list of the IDs of the people followed by the person with ID j. So, for example, if j is 135, this is the list of the people that the person with ID 135 is following. Two people, 136 and 234. The question we need to answer is this: which two people in the network have the largest set of people in common on their two lists? Let me illustrate this with an example. Let's say Joe, whose ID is 2, follows 13 people. And let's say Jane, whose ID is 2,998, follows 11 people. And let's say further that 7 of these people are on both lists. Well, if no other pair of people out of the entire list of 3,000 are following more than 7 of the same people, then the answer to our question is Joe and Jane. Or in terms of their ID numbers, the answer is 2 and 2,998. As it happens, I have a 3,000 element cell vector whose elements are vectors of integers just like the one in this schematic. And its name is follows 2. And it's stored in a mat file named follows. Let's clear the workspace and load it. And let's look at the workspace. And there's follows. It's a vector of length 3,000, and its class is cell. And since there are 3,000 people on this list, that means there's 3,000 times 2,999 divided by 2, which is just under 4.5 million pairs to look at. That seems like a lot of work. But, well, we've got MATLAB. And here's our MATLAB function. It's called max same follows v1, and the v1 is for version 1. It visits every pair of people in the network and returns in the output argument named people the IDs of the pair whose lists have the largest number of common IDs. It also returns as a second output argument named follows a vector containing their list of common IDs. The function looks at each of the almost 4.5 million pairs by iterating in the outer loop, whose index is II, from the first ID to the next to the last ID. And then in the inner loop, starting from II plus 1 and going to the last ID. This device of having a nested loop structure with the outer loop stopping one short of the end and the inner loop starting one past the index of the outer loop is a standard way to enumerate every pair of distinct numbers in a list. Initially, the output vector people is empty, and the maximum number of people being followed, which is kept in the variable numFollows, is set to 0. Then, as the nested for loops pass through each pair of IDs, the function uses MATLAB's built-in intersect function to find the list of common elements in the two vectors with those IDs and store it in tempFollows. If the length of the resulting intersection is greater than numFollows, it replaces the IDs in people and copies the list of common elements in tempFollows into follows. For the sake of simplicity, we ignore pairs that have the same number of common elements as the maximum we've found so far. So if multiple pairs have the same number, this algorithm will find only the first pair it encounters. Let's time it. I'll cut out some time for you. Our function is surprisingly slow, but again, it's an order n squared algorithm. In fact, it's order n cubed in the worst case, because the intersect function is linear by itself, and the follows list could be close to n if everybody follows everybody else. And don't forget that we need to look at over 4 million pairs, and that takes time. Let's look at the output. So number 293 and number 1096 had these elements in common. Looks like there's 8 of them. So, it takes a long time, but are we doing any unnecessary work? The answer to that question isn't as obvious as it was in the previous example, and the answer is also a bit fuzzy maybe. Here's what might happen in practice, and probably will happen many times. Let's say we're at a place during the execution of this algorithm where our current candidate pair follow, say, 5 common people. Then from that point on, we shouldn't even consider any person who doesn't follow more than 5 people, because there's no way that this person could be part of a winning pair, right? So we could save time and skip this person. Well, here's how we can change the code to take advantage of this insight. We've changed the name to max same follows v2 for version 2. And we've added an if statement in each of the loops to skip these losers. If you need to, feel free to stop the video to convince yourself that they should be skipped. In any case, whenever the if statement identifies somebody who cannot possibly be part of a winning pair, it terminates the current iteration by means of the continue statement. The continue statement is very similar to the break statement in that they both cause the current iteration to end without further computation. But unlike the break statement, which quits the loop entirely, the continue statement quits just the current iteration of the loop and continues to the next iteration. If it's in a nested loop, it quits only the loop it's in, not the surrounding loop. It jumps to the end of the body of the loop, and unless it was the last iteration, the loop continues with the next iteration from the top of the body of the loop. Let's see whether it helped. Wow, it helped a lot. That's over a factor of 60 improvement. And we got the right answers. A word of caution is in order here. Unlike the modifications that we made in the previous example, this modification may in some cases not help at all. Whether we save any work here is entirely dependent on the data. As you can see, in this case, the solution has a vector of 8 elements. If every person in the social network had at least 9 friends, then the if conditions would have been false in every case, and we would not have saved any time at all. In other words, the worst case execution times for both versions of the algorithm would be the same. Nevertheless, this technique can be very useful in practice. The general idea is that if and when you realize that there's no need to continue the current iteration, you should skip the unnecessary work. It can save time. And the general idea of this lecture is that to increase the efficiency of your algorithm in practice, you should ask yourself whether it's doing unnecessary work. One way to reduce unnecessary work is to avoid repeating the same calculations by storing the results of the calculations in auxiliary variables, typically calculated in auxiliary loops. A second way, which is also an especially easy way, is to avoid repeatedly copying arrays into larger sizes by pre-allocating them. And a third way is to take advantage of the characteristics of the likely input to the program in order to identify calculations whose results are guaranteed to be unused, and then add auxiliary conditional statements to identify them and skip them. And in all cases, it's always especially important to focus on those portions of the code that are computationally intensive.